Good evening, everybody. It's great to see you all, and I'd particularly like to thank all the friends of the KITP here for their support of the Institute. If you'd like to know more about becoming a friend, there's information outside there on the table, or talk to any of us. It's a great pleasure to have our speaker tonight, Clifford Johnson, with us. Clifford did his undergraduate work at Imperial College in London and PhD at University of Southampton, so coming from the UK, before moving to the United States for postdoctoral work and faculty positions. And he joined the physics department here at UCSB last year, right? Very, very recently, and it's great to have him. Beside his theoretical physics work, which spans string theory, gravity, quantum gravity, and black holes, Clifford is very well known for public engagement in science. He talks to writers, to artists, to filmmakers of all kinds, and gets them talking about science. Now, I'm sure you're all quite familiar with Clifford's book on D-brains and have mastered the material in there. So you're now ready to move on. Clifford has a very new book, The Dialogues, talking about science, and you can get a 30% discount published by the MIT Press by getting this sheet outside and scanning it. Okay, so with that, I think let us talk about science, and welcome, Clifford.
Thank you. Well, first of all, it's a pleasure to be here and to have met many of you and spoken with you during the reception and maybe a little bit afterwards as well. I'm being deliberately playful with the title, as you may have guessed, and you're probably going to guess what's on the next slide, which is something to do with, right, yeah. So what was it? 1999, this movie came along that really, of course, it didn't invent the idea, but it very much placed it in the popular domain, the idea of something about our world being a construct in some way, something about and the idea I want to get at today is that the space and time in which we live is just a sign of something more, there's more structure underneath that we can't see. And there's evidence for this, at least on paper, in terms of the calculations that we do here at the KITP and other places. It is kind of amusing. You will see a matrix appear, hopefully, before the talk is done. And we can ask the question, do we live in a matrix, the matrix, whatever that means. I'm certainly not going to go deeply into any of the philosophy associated with such ideas. And the whole construct is really coming from a physicist's perspective. So I hope you're not expecting a philosophy lecture. There's the movie poster. There will be no kung fu in this talk, and definitely no shooting or anything like that. So, is there something deeper underlying the space and time in which we live, which is the sharp question, which we can ask from a physics perspective? And if there is, what is it? So that's what I want to address today. And I'm going to start with a little bit of a cautionary note. Because what I could do is just give a talk with lots of pretty pictures. And of course, there's nothing wrong with that. What I really want to do also is give you a sense of what's going on, what we really do when we think about these things. What do our calculations look like? So there's going to be equations. There's going to be some pages of the notebooks that we might see. Despite what you may think, we don't just sit around drinking coffee and chatting all the time, although there is a lot of chatting and drinking coffee. We also calculate. We also try and answer these questions with real calculations. Then we hand over those ideas to the people who figure out what kinds of experiments would test these ideas, and so on and so forth. So I'm not going to be ashamed to show you some of the steps in how you might think about these things. So you have a choice. You can just check out because equations have shown up. Or you can go, it's okay if I don't get everything that's on the slide, because I'm also saying things that are not the equations. And so immerse yourself as much or as little as you wish in the content that you'll see. In the spirit of the movie, it's, I guess, a choice between the red pill and the blue pill or something like that. How deep down the rabbit hole do you want to go? So speaking of rabbit holes, let's talk about what we all probably had some version of on the wall in school, which is the answer to the question, at least at that level, what's everything made of? And we have the elements, the visible matter that we've experimented with over the years. And there's this lovely thing showing all of the lovely patterns that emerge when you try and figure out what the world is made of, and these various kinds of elements. And it's really great to have these kinds of posters. This is a standard poster that you may find on a wall in school. But then you know that there's underlying, or maybe you've heard there's underlying some idea that actually you can go a little bit deeper. Those patterns have an explanation because what's going on is that there's an atom. These are different kinds of atoms. But those things are, in some sense, the result of some underlying structure, and what we have is a cloud of electrons. I've sort of drawn that as blue, and some sort of nucleus, but then you dig into the nucleus and it's made of things called protons and neutrons, but then you can dig into those and find those things are made of quarks of various kinds. And this is not a talk about the details of particle physics, so I'm not going to go too far with this. I'm going to just show you the summary, which may be up on the wall, if not in your high school. Maybe you saw it somewhere. Definitely it's up in physics departments at college level. And what that shows is the standard model, what emerges when you look into all of those details. The quarks, the electrons, those things fitting together in different patterns. They give you the periodic table of elements, but they themselves fit into patterns in terms of how they're classified. And the standard model of particle physics tells you about all the interactions we understand that we've seen, the four forces of nature, and how all the different particles, the up and down and strange and charmed, and all of the funny names you've probably heard about that quarks have, and the different kinds of electrons, electrons and their cousins, the neutrinos, and their siblings, the tau and the muon, and things like that. So it's all on this poster, and it's a nice thing to have. And you can also order this from the Department of Energy, or I think it's the Department of Energy poster, yeah. So we're going to come back to this poster. Let me actually just see if I can remember how to... no, that doesn't work. Okay, never mind. The point I wanted to emphasize here is that this all comes about from studying quantum physics. But before I tell you what that is, or before I remind you what that is, I want to tell you about classical physics, sort of the Newtonian physics that we're familiar with until that burst of activity that happened just as the 20th century was breaking, which led to the understanding of the quantum world, and ultimately that whole poster is founded on. So one way of formulating Newtonian physics is through something that is sometimes called an action principle. And this is not very often presented in public talks, so you may not have encountered this. So I'm going to go through it fairly swiftly, but hopefully getting you the key ideas, because it's going to underlie some of the things we're going to do later. So I have a particle. It's moving. It has some speed in some particular direction. That's a velocity. I'm going to call that v. That's some velocity. It doesn't matter what it is. It just has some velocity. Associated with that, then, is some energy of motion, kinetic energy. I'm sure you've heard that term before. And that comes, you build that out of the particle's mass, m, and it's the square of the velocity. You multiply those together, and there's a factor of 1/2 as well. So that's the kinetic energy. Now let's imagine it does this for a little bit of time, which I'm going to call t. Okay? So it moves at this speed with this energy for a little time t. Well, there's a new quantity we can build from this, which is I multiply the two things together. And it's called the action. And I'm going to call it I for no good reason. There's another term that's usually used, another letter that's usually used, but I'm going to need that letter later on, so I'm going to call it I. Okay, so that's just moving for a little bit of time. What I can do is I can actually build up a quantity, an action associated with the whole trajectory of a particle as it moves in space. And I can do that by basically adding up little bits of what I just did there. So a little time t, a little bit more, and so on and so forth, and I can go ahead and do that. So I work this out for arbitrary paths by breaking it into little pieces. So there's a little piece, there's another little piece, etc., etc. And I can build it up. So any path I can do this for, and I can compute a number, which is the action of that path. Hopefully that makes sense. You actually need to do a little bit more, include not just kinetic energy, but also potential energy. If there's a force acting, let's not worry about that for now. Just have the idea that a path is associated with an action. And then Newton's laws of motion are easy to state. They simply say that I just take the path that has the least action. That's pretty simple. It actually is a very elegant way of formulating physics, and will be extremely useful when I come to tell you now how quantum physics can be thought of. So let's start with quantum physics. So the point, one way of thinking about quantum physics is that there's a constant of nature that we'd missed, which is called Planck's constant. That's Planck's constant divided by 2 pi, but don't worry about it. You can see in the units I've written it, it's a very, very small number. And so we basically missed it because you have to sort of do things that know about that sort of amount of smallness. So what do I mean by that? Well, Planck's constant is, it's measured in the same units that the action is, energy times time. And so nature has this fundamental constant that is a basic unit of action. And what that means is that if I have physics going on that has amounts of action associated with the physics that's comparable in size to this small number, then the classical world is no longer the right description. Then things are very quantum. And we missed it for thousands of years of doing physics and observing our world because the sorts of things, sort of large objects moving large masses with large amounts of energy and so on and so forth, have huge units of amounts of action which are way bigger than this tiny amount. So we just don't notice the detail. But the point is, when we started looking down at the structure of atoms and things like that, these tiny particles have tiny units of action that are comparable to nature's unit of action, and so we see that it's sensitive to the quantum physics. So we have to reformulate physics in a different way. What we do is we formulate it as what's called a sum over paths or a sum over histories, which is going to be a little bit intriguing, I hope. What you do is you have to consider, just as we did before, all the possible paths that a particle can take, say, going from one place to another. And what I need to do is I need to work out the action, just as I did before, for each of those. What you do to compute the outcome of some process, like moving from A to B, is you have to add up all the possible paths it can take. And you weigh them by some number, which essentially comes from the ratio of the action to nature's basic constant. Don't worry about the details. It's some number that's built from that. For those of you who do know, that's e to the I, Euler's constant. I exponentiate it in some way. But there's some number associated with all those paths, as I said. And you basically formulate quantum physics by saying all the possible paths are allowed, but some are more allowed than others. It comes from this weighting. And when you add them all up, it tells you essentially the probability for that process to happen. So that's how you formulate quantum physics. Seems a little bit weird. It's very different from how we think about things in the Newtonian way, but you can see it's built out of the same kinds of objects. And the key point is that it works, and it works spectacularly. Now, you can even do the kinds of things we talked about with the particle interactions that were in that poster in the same way. So I'm now going to show you a diagrammatic tool that physicists use to keep track of how those interactions work. So, again, let's look in the notebooks of our theoretical physicists. I'm going to use symbols again, and I'm going to pick a particle. Let's say the electron, right? That's very familiar. Governs all the electronics that you use every day, for example, and all of chemistry. And then it interacts with the particle of light called the photon, and that's actually how the electromagnetic interaction is imparted between particles. So let's actually model that with this language. So what you do is you draw a diagram. So just as I had the action previously for a particle moving, I had a velocity and another velocity. So it kind of went like the square of the velocity because it was the kinetic energy. Well, the action that you would compute for this process has the particle symbol is psi, and that goes like psi squared. The photon has a symbol. I'm going to call it A, and that goes like A squared. Then what I do is I draw a little line, and annoyingly there's no post. Ah, here it is. Yes. I draw a little line for this particle moving along, just like I had that massive particle moving along with some velocity. But now it's the electron moving along. There's the photon moving along. And basically, that would be it, except that they can interact. So there's another piece of the diagram I must draw. This thing here. And so you can think of this as this moving along, and then it emits or absorbs a photon and then carries along on its merry way. And that's interaction. So there's a term in the action, when you're computing, the rules for computing the action, that has a psi squared, because there's two of them, and an A, there's one of them. So A squared, psi squared A. And those are the rules. They're actually called the Feynman rules. These are called Feynman diagrams, for those of you who maybe have read some of these kinds of things. So the force of interaction for electromagnetism, two charged particles, electron and another electron interacting with each other, is they exchange a photon. And in fact, in particle physics, all interaction works this way. And it's one of the things that underlies the beauty of that poster that I showed you before. And you can compute numbers associated with these interactions by using that A squared from this, and then there's a psi squared A and a psi squared A and so forth. And it's a way of computing numbers. Now, the point is, though, that that's not the only diagram you can draw. You can draw any diagram you can draw with these rules will contribute to the physics, because that's the summing over parts. So we should do that. So quantum correction, the quantum contribution to these two particles interacting, would be a diagram that looks like that, for example. So it emits a photon off to interact with its other friend, but before it gets there, that photon splits, turns into a particle, and actually this turns out to be the antiparticle. It's sort of as Feynman had noticed years ago, the electron going back in time in a way, and it's this antiparticle, and then they recombine and turn back into the energy of the photon, and then meet that particle. So that's an allowed path, and the same sets of rules will give you numbers associated with these three basic things. So I can build any diagram. Here's an even more complicated one. And if you begin to drift off in the rest of the talk, that's okay. You can have fun doodling diagrams. Just try and draw all the diagrams you can draw for any process you want to make up. And it's kind of fun to do. And we're going to play with these kinds of diagrams later on. So you might discover some things drawing some diagrams ahead. So that's quantum physics from the point of view of particle physics. And other kinds of particles and other kinds of forces are modeled in the same way. You have a different particle being exchanged here for, say, the nuclear forces, the strong nuclear force or the weak nuclear force, and so on and so forth. And quarks and electrons and neutrinos and all of these wonderful things interact with those rules. The actual thing underlying it is something called quantum field theory. And as I said, it's incredibly successful. We do these collider experiments you've probably heard of. For example, that's the LHC at CERN in Geneva. There isn't a big yellow stripe through the countryside. That's just showing you where it is underground. and there's one of the, a part of the CMS experiment. And there's an example of a collision of particles that happens in the experiment when it's running. And all of those tracks of particles coming out of the collision are confirmed to obey the rules that you deduce by computing with those diagrams I showed you to remarkable accuracy. This arguably is one of the most successful theories in the history of humans trying to understand how nature works. We can compute, to the, 12th, 13th, 14th decimal place level of accuracy, and we can do experiments that confirm that to that accuracy. And so it's quite remarkable. Excuse me. This is a little out of date now, but it's still striking. Feynman compared this to the business of being able to specify the distance between New York and Los Angeles to better than the width of a human hair in terms of the accuracy that you're doing when you talk about those decimal places. So let's notice something very interesting here, because there's new opportunities here, there's new physics that comes about from this as well that you may find unexpected. Even nothing is interesting in the sense that I'd like to explain now. So I talked about a particle and an antiparticle, which we saw previously. A photon can turn into an electron-positron pair or vice versa. And that's part of the picture of that poster, that well understood in that poster that I talked about. But there's also the possibility that the vacuum of space can make this kind of thing happen without us actually doing anything, without producing some particles at the outset. The vacuum will produce them itself. And so going back to our notebook, we have the idea then that we have this thing that we think of as nothing, this empty space. But there can be a particle and antiparticle, let's say an electron and a positron, which are equal and opposite. They cancel each other out, and all you have left is the energy of, say, in a photon, equivalent to the mass that they had. But in this case, I started with nothing. I have an antiparticle and particle pair popping out of the vacuum. We need to talk about where that energy came from in a moment. They dance around for a little bit, and then they annihilate again and give that energy back. And you end up with nothing. So the vacuum of space is seething with possibility at the quantum level, which is a consequence, an immeasurable consequence of this whole framework. So how likely is this, right? You might ask. And again, you can borrow some energy, E, equivalent to their mass, for a little time t, again, if that product, energy times time, is of order nature's basic unit of action. So that's how that works. And you can measure this effect, and it's very important in how we understand nature. The Feynman diagram for that is just a loop like that. If you read it with time running this way, it looks like there was nothing, and then something goes that way and that way. They circle around for a while and then go back into each other. So that's how you read those diagrams. But of course, we want to talk about space and time, so let's talk about gravity. Let's go back to the poster. Let's zoom in a little bit. Let's look at the gravitational interaction part, and it says something a little bit embarrassing. It says the particle of exchange is the graviton, but it's not yet observed. And so that's a bit of a hole in the poster. What actually happens if you try and do the process I just talked about? You try and model gravity at the quantum level by exchange of some particle called the graviton, say. It seems, doing it with particles, it seems to fail. And you might go, well, that's not a big deal, because Einstein sorted out gravity, right? It's all about geometry. So let's talk about that. We'll come back to the quantum stuff in a moment. So gravity is geometry. Let's think about that for a moment. Well, looking in our notebooks, we can see what the setup is. We have time. And just for simplicity, I've removed 2 of the spatial dimensions, but you're aware that there's more than one. But you can imagine walking in this direction. That's the space direction. Time goes by. You'd measure that with a clock. You'd measure this with a meter rule or something like that, or a yardstick. But the idea then from relativity that you've probably heard is that space and time should be thought of as connected into one object, this whole sheet here, which I'm going to call space-time. And essentially, what we learned from Einstein is that space-time itself is a dynamical thing. It can change its shape and its geometry in such a way as to be part of physics. It's not just the place we put our stuff. It also, you know, the analogy I like to give is that it's not just the arena in which physics happens. The arena is part of the game as well. And so it can change shape. And we need to understand that at the quantum level, and we're going to talk about that in a moment. But right now, let's just be aware, especially if it's maybe the first time you've heard this, this is not a weird speculative thing. This is how the world works. And the force of gravity gets rethought as a result of space-time being curved. So we have the usual picture of something being attracted. There's a mass, maybe a planet. There's another mass, maybe it's satellite, the moon or something. And it's being attracted by the force of gravity as it moves along and its path bends. But instead, what's really going on, we learned from Einstein, is that this thing is bending space-time in a way I've sort of tried to depict here. There's space-time being bent in such a way that this particle is just trying to follow what it thinks is a straight path, and it ends up being curved because it's moving on a curved space-time bit of space-time due to the presence of that mass. So that's how gravity ends up looking, and it's, of course, again, something I should tell you is something that works exceedingly well. Some of the early tests of it were just trying to understand the motion of planets in our solar system. The Newtonian rules for how planets move work pretty well, but actually when you get, quite strikingly, to Mercury being very close to the Sun, its path actually wobbles quite a bit compared to what Newton would predict. And that was a big puzzle for a long time until Einstein reformulated gravity and realized that there are severe deviations from the Newtonian physics that explain the motion of Mercury. Very topically, I think recently there was something happening in the sky in some parts of the world near here. And that allowed, in addition to being a wonderful thing, a total eclipse, it's also great for testing relativity, because what happens is that you have a nice thing in the way of the sun, so you could look just past the sun at distant stars. The light from those distant stars, as it passes near a massive body, will get bent according to the rules of the bending of space-time, what have you. And you can calculate what that is and actually see whether it matches. And one of the big triumphs early on in 1919 was the confirmation that the bending of stars seen during the eclipse that year matched what had been predicted by the relativity theory. And of course, A lot has happened since then in terms of testing the curved space-time picture. We understand our cosmology, the evolution of our whole universe is understood in terms of it being space-time that is expanding in a particular kind of way that you can write equations for and study the different epochs of physics in the universe that take place because of that expansion. And I don't have much time to talk about this lovely poster, but over the 13.8 billion years of the universe's existence, a lot happens to space-time in the global and the local, as I'll talk about in a moment, and we can test things there, and it all works rather well. Now, the local leads me to talking about galaxies. Generically, galaxies are now well understood in modern terms to depend on the presence of black holes in the core of the galaxy, powering a lot of the activity that's going on there. Most notably, again, from the news, you may have heard that we're now taking pictures of black holes in the cores of galaxies. There's M87, very active galaxy not too far away, and the Event Horizon Telescope, which is what that is actually shorthand for lots of telescopes working in concert to essentially make an observing dish the size of the Earth itself by having lots of telescopes around the Earth coordinate their measurements, are able to deduce many things, including effectively a picture of what's going on with the black hole there. The black hole at the core of our own galaxy has been imaged in a similar way. This all relies on general relativity working spectacularly well. And finally, this is a simulation, which hopefully will work. This is a simulation of two black holes orbiting each other. You can see the light from distant stars being bent, according to general relativity, as it passes by. But the thing I want to talk about is the spectacular event of these black holes themselves actually colliding into each other, merging into each other, as these will eventually do, and forming a black hole. And you may have seen a little tremor of the whole arrangement there. What actually happens is that there are ripples in space-time itself, because it's flexible and bendy, as we said, that go out into the universe as a result of that event, and we can detect them here on Earth. And so what you see here are examples of some of the events that have been gathered, measuring the properties of, here's a black hole, here's another black hole. You can work out their masses, and then you can work out the mass of the black hole that formed from them colliding. And there are many, many, many more of these events than I've shown here, and this is now becoming quite routine in the kind of physics that we do. So black holes, which are one of the most spectacular predictions of the curved space-time picture of general relativity from Einstein, those are are well understood in terms of general relativity. I keep talking about black holes. Let's actually work out what one is. So let's do a calculation. Let's look over the shoulder of the theorist. And what do we have? Well, this leads us to something that's quite topical here in Santa Barbara, is the idea of escape velocity. I say that because it seems routinely every week now there's a rocket going up, and we all look at it, right? So that thing is going into orbit, and it has to fight against the fact that the Earth is pulling it back. Now, what I'm about to tell you is not quite what the rocket does. The rocket has a smarter way of going into orbit than what I'm going to talk about. But the idea of having to go at speed in order to get out of the gravitational pull is something that's nicely illustrated every week at Vandenberg for us. What really is going on in the simple case, it would be a calculation like this. I have the Earth, which has some mass I'm going to call m, and I'm some distance away. I have another mass, little m, a distance r away from the center of the Earth. there's some energy associated to the force of gravity binding you to the Earth. And that energy turns out to be the product of the masses divided by the distance you are away. And so less binding if you're further away. And then there's a constant of nature, which is Newton's constant, called G. So what I need to do, if I were just to take something and try and hurl it away from the Earth with some velocity, I need to give it enough kinetic energy to trade, I need to trade that kinetic energy for the gravitational energy. So I need to write this equation, is what I would do. There's the kinetic energy. So I can solve that equation to work out what is the velocity I need given my starting distance and the masses and so forth. So let's simplify. Let's start at the surface of the planet, which I'm going to call a radius capital R, and I can solve the equation, and there's an equation for the escape velocity. Now, it doesn't matter if you don't understand the details. The key point here that the equation tells you is that that escape velocity is much larger if the mass of the planet is larger, which seems reasonable. But also, if you keep that mass the same, but you compress it into a smaller space, decrease r, that would also increase the escape velocity. A more compact object has a higher escape velocity is the takeaway. This is perhaps a nicer way of visualizing it. There's the radius, and there's the velocity. The smaller the radius for a given mass, the higher that velocity I need to get away. Okay. Well, let's actually calculate it for the Earth, and you probably know these numbers. Or maybe you know them in other units, but there they are. Okay? So you get 11.2 kilometers per second, or if you prefer highway units, it's 25,000 miles per hour. The Vandenberg rockets do not go at that speed because they can... I'll tell you if you ask me. Okay. But that would be the escape velocity if you were just going, you had one shot at it, and you need to just get up to speed and sort of throw the thing off the planet. Okay, so we can ask another question though. What if the radius was small enough that that escape velocity approached the speed of light, which, as you probably heard, is the fastest anything can go in our universe? Well, you can compute that, and it turns out for the Earth, that radius, which is sometimes called the Schwarzschild radius, is about a centimeter. So if you took the entire mass of the Earth and squashed it down into a little ball about a centimeter across, then if you made it any smaller, light would not be able to escape from it. And so we arrive at the idea of a black hole, compact objects for which the escape velocity exceeds the speed of light. And so the terminology people use is, well, there's that anything inside that radius would not be able to escape, so that's called the event horizon. And that is what's called the Schwarzschild radius, where I've now put c, which is the usual symbol for the speed of light, into the equation. Okay. But of course, quantum physics is going to tell a different story. So remember that business we talked about, the fact that the vacuum can produce and is producing all the time these fluctuations, these possible particle-antiparticle pairs popping into existence, in and out of existence everywhere. Let's do that near a one-way door, which is the event horizon. Okay? And if we did that, there's a possibility that this one falls inside the black hole, but the other one doesn't. This is just a piece of the event horizon. Okay? In which case, that particle would be able to fly free and be detected, you know, off in somebody's telescope or something like that. Okay? So we found a mechanism by which we get around that first line. And it produces radiation. This was discovered by Hawking. This is called Hawking's radiation. And if you do the analysis, you'll find that the radiation coming off that black hole is, in fact, thermal. It's like it's like heat, and in fact, it has a particular temperature that you can compute. I just put the formula there. don't worry about it. I just put it there just to, for completeness. And so that's kind of interesting because it's a remarkable formula that uses things to do with relativity, special relativity, general relativity, gravity, and quantum physics. A remarkable equation and a remarkable conclusion. Black holes must lose energy. There it goes. What's the end point of that? We don't know. It's a big puzzle. In fact, some of the consequences, some of the naive consequences of following this process all the way to the end violates some of the things we think shouldn't be violated in physics, and that leads to things like the information paradox and things like that that you may have heard of, which I'm not going to talk about today. But this is an urgent thing to understand. Now, I should say this Hawking radiation itself is a tiny, insignificant effect for astrophysical black holes, because there are many other kinds of effects going on that are at higher temperature. But it's still really important to understand why there's this puzzle in physics that we haven't yet figured out. What is the full story of quantum gravity can help us understand this, and various other things that hopefully I'll mention shortly. Not just in the issue of black holes, but also to the issue of the very early universe, where again, quantum gravity effects seem to be important there, and in fact, turn out to be the seeds of the structure that give rise to us 13.8 billion years later. So this is part of the story of some of the things people are talking about and discussing here at the KITP on a daily basis with one of the workshops that's going on, and even when there isn't a workshop. What is the full description that this calculation is trying to tell us about? Okay, so like I said, they behave like thermodynamic objects with some temperature. You can actually go and check that. There are other quantities that thermodynamic objects should have. And for example, it turns out you can compute an entropy for black holes as well. Now, I don't have time to tell you much about entropy, except to say that it's something to do with the fact that we have, I think I have it in my list of questions actually, the fact that when I talk about thermodynamics, I'm usually talking about, for example, the temperature in this room. Now, we know that this room, the air in this room, has another description. It's made of lots and lots of tiny particles. And when I talk about the temperature, what I'm really talking about is the average energy per particle over all the many, many particles that make up the air. And, but it's a very, very useful measure, sort of a macroscopic measure of what's going on microscopically. Now, also, there are other things like the entropy, which tell you things like, well, how many ways are there to distribute the energy among all the many, many, many particles in such a way as to give me the same temperature that I measure that one number. And so that's a way of counting how many microscopic states are there that correspond to the temperature. And so that entropy is a very important thing, but if you compute an entropy for something, you've got to wonder then, what's the other description? Is there some microscopic description going on? Another thing you might think about is water. All right, so we talk about water, we talk about its fluidity, we talk about its temperature and things like that, but we know it's also made of molecules. And all of those things are the effects that emerge when you have lots of molecules working together, and somehow they give rise to fluidity and all of these nice things that we associate with water. But no individual molecule knows what fluidity is. So there's an interesting opportunity here to ask the same question about space-time itself. We've seen a hint here that there's thermodynamics emerging for things like black holes, which we think of as large macroscopic objects, but it's suggesting that they and space-time itself are built of some quantum bits, particles, other components, like the water molecules that we're trying to find. So what is this physics? And this is the quest. This is the quest of looking for quantum gravity, and this is really the beginning of the answer to our question right at the beginning with the matrix, which is that, is there something underlying? There are strong hints that there are. Space and time, maybe, space-time, is built of something else, sort of molecules of some kind. This sort of nice, smooth gently curved space-time that we deal with in astrophysics and so forth is somehow an illusion created by all of the busy stuff that's going on at the microscopic level. Okay, let's explore that. How would we even formulate a theory of quantum gravity to do that? So, well, let's do what worked before. Let's try a sum over histories, a sum over paths. But now we have to be a little bit more bold. So there was the whole sum over histories thing. We computed an action for every possible trajectory. But now the dynamical thing is space-time, and it can change its shape. So what we should do is perhaps sum over all possible space-times for a given process. Now, it's really four-dimensional, 3 plus 1, but I can't draw 4 dimensions very well, so I'm just drawing 2, as I've been doing. Okay, but I need to sum over different possibilities, different shapes. There's a sort of a lumpy bit there, there's a bit like that. I might even try and include the possibility that the topology of space-time can change as well, because that would seem a natural feature that might be dynamical too. What do I mean by topology? Well, it's, for example, the difference between an apple and a donut, for example, if you were considering your breakfast options. There's a sphere. And you can imagine if this were made of modeling clay, I could add a little handle to it, like a cup handle, and then it would be more equivalent to this thing, which has a hole in it that you could thread something through and it wouldn't be able to come off. So that's topology. And what physicists do is they try and sum over all geometries and topologies in some way to see whether we might be able to get something that models this quantum physics we're seeing of black holes. And there's been recent progress. So this is what I want to end with. There's been recent progress in doing this, which has been very exciting, and the consequences of it have been trying to be worked out, for example, in the workshop here, and so on and so forth. So for some kinds of black holes, you can do this. In general, it's extremely hard. Geometry is a hard thing to do in 4 dimensions, especially when it's made of 3 space and 1 time, and you're considering all possible geometries. You have to classify them. You have to figure out rules for giving a number to every possible geometry and every possible topology, and it's a huge mathematical problem that is unsolved. But in some cases, for certain kinds of black holes, a nice thing happens, for at least some of the physics. And what happens is that there's a symmetry for certain kinds of spherical charged black holes. That means that the space-time is effectively 2-dimensional. What happens is that as I approach this thing from any direction, because it's spherically symmetric, all directions are the same, essentially there's not as much interesting dynamics in worrying about things changing as I move around the surface of the sphere. So the only interesting physics in that sector comes from time and moving radially. And if you study just those 2 pieces of space-time, you can make some progress. And so this is what it looks like. And this is in the wrong order. Okay. So we have to do what we did before. Take a bit of space-time, and now I have to break it into pieces, just as I broke those paths into pieces. So I need to break it up into pieces, and what I'm going to do is I'm going to use triangles. So I'm going to take little equilateral triangles, and I'm going to draw little ones and break it up into pieces. Later on, I'll take the triangles very small so that I can make any sort of smooth space-time that I want, but I'm just drawing this for you. And you can even model sort of little bits of curved bits by having different numbers of triangles arriving at each other at a point, and so on and so forth. So it's a fun geometry problem, and you can actually make some progress. But what you need to do is find a way of tessellating, right, breaking up into triangles, all possible geometries and topologies, and then adding them up with some rule, just as we saw for paths, because that's how quantum physics works. And here's a bit of what that looks like. So there's a little piece. You imagine this is made of equilateral triangles, then you can immediately see that this really looks like there's some bits that are sticking out at you or going into the board and so on and so forth. You're seeing some of them at angles, and that's why they don't look equilateral in this projection. So if you use enough triangles, you can make a shape, any shape, for a two-dimensional space-time. Now apply the following rule, just for fun. Decorate in this way. Draw those blue lines for every triangle, and you'll get this. But now I'm going to ask you to look back in your notes at something we did earlier, because this actually looks like one of those diagrams that we were doing when we were colliding electrons and so on and so forth. In other words, it looks like there's a quantity, I'm just going to call it M for now, that has a rule that says it moves along, and so that's what those lines are, and then they can actually split into three. That's what this line is. I can build any of that blue diagram with these two rules, and the action would have a sort of M squared and an M cubed, just following the kinds of algebra we did before. You can actually follow your nose. And the reason this is good is because we're very good at summing these diagrams, right? It's the basis of all of particle physics, and so we know how to do this. So if we can sum all the possible diagrams, because of the equivalence via this, we can capture all of the possible manifolds. There's a little bit of a wrinkle, and that comes to that comes to the question of what is this thing M? Well, it's actually a matrix. So what is a matrix, in case you're wondering? Well, it's an Excel spreadsheet, as it were. All right? You have rows and columns, or it's like a grid reference on a map. I need two numbers to go north, south, east, west, that sort of thing. Here's an example of a matrix. This would be a 4 by 4 matrix. It's a list of numbers. There's rows and columns. The notation we use, just in case you're curious, is to label rows and columns by I and J, and then you say M, I, J. M32 would mean go to the third row and the second column. Oh, it's 51, it's a number. So instead of it just being numbers like a velocity, it's an entire matrix of numbers. I'll tell you what to do with that in a moment. So the diagrams that I drew before, they actually carry information about the I, J labels of the matrix. They're sort of ribbon diagrams in a way. And these ribbons are rather nice. Now, in the details, the allowed M's are certain kinds of matrices called Hermitian matrices, and I'm not going to use 4 by 4 ones. I'm going to use some that are some number n times n, and I'll specify what n is in a couple of slides. But 4 by 4 is a good placeholder in your mind for what it looks like. Okay, let's keep going. So ribbons, good. The ribbon diagrams then, let's draw a few. So I'm just going to draw a very simple one, okay? And you can see it uses the rules I had before. There's something moving along, and then it can split into three, and I've drawn a very simple diagram like that. I could decorate it with triangles to go back to the triangle, and that would give me a very, very poor tessellation of a sphere, it turns out. I'll let you think about that. If you cut two triangles and try to glue them together, glue the edges together, it would make a very, very, very bad sphere, but we'll do better in a moment. I can actually draw a more complicated one. I can add an extra leg. It's up there. That would also be drawn on a sphere. But I could have added that leg in a different way. I could have added it in a way that goes to the inside of one of these loops. And that actually can't be drawn. That actually does not tessellate a sphere. It actually tessellates a donut. So I'm going to leave that as an exercise. But the point is that if you didn't have this ribbon structure, you wouldn't be able to distinguish between these two diagrams. You wouldn't be able to keep track of topology, which is important. So that's the point. Okay. I could say more, but we should move on. Okay. And you can just check that you can draw this on a torus, and there's no way of putting this on there without breaking one of the ribbons. Okay. Time is short, so I'm going to tell you the end of the story. So to get smooth geometry, I need lots of tiny triangles. So there's some triangles, there's a very bad sphere, right? I could try and squash the ends a little bit if it were made of modeling clay or something to make it a little bit better. Or I could do, if I only have triangles, then I could use more triangles. Let's make it a bit better, right? dodecahedron, sorry, icosahedron, or I could go better and better and better. If I use more triangles, I can make smooth geometries. Now, we're not just doing spheres, we're doing all two-dimensional geometries in this problem, but I just showed you a sphere as an example. This turns out to be equivalent, asking for tinier and tinier triangles to give me smoother and smoother geometries, because I want to model space-time, turns out to be using larger and larger matrices. That n by n matrix, n becomes large. And so I have a matrix where I have many, many numbers going back and forth, and that should remind you of something. Right? Again, from the movie, right? So there you go. It certainly reminds you of that. And that's what one of these large matrices would look like. N gets very large. I'll tell you how large in a moment, in both directions, rows and columns. And somewhere in there, it turns out it works. If you actually build this kind of model very well, it does give you a nice model of space-time, and it does actually allow you to model properties, these quantum properties of black holes, and actually give the answer, at least in this model, to one of the basic questions we asked. So, for example, this entropy, which is a very large number, it's the area of the black hole, divided by a very small number and another very small number multiplied by a very large number cubed. So it's a very big number. And that turns out to go as the logarithm of the size of the matrix, which itself is very large. And that matches quite nicely. This is a formula that Boltzmann would have written, in fact, did write way back centuries ago in trying to connect thermodynamics to the properties of microscopic things. So this actually comes out of this kind of model. So the microphysics then seems to be the discrete elements of the matrix, and in this model at least we have an answer to the question of what underlies space and time. So the question is, could this be true more generally? Smooth space-time emerges then as some illusion, if you like, coming from the details of all of those tiny things inside the matrix working together. So the summary then is that this was great to see. It was very exciting for us to see this kind of model work out. There are other examples of this kind of physics coming from large matrices in certain kinds of ways, which is very nice. And you could ask, well, does nature work this way? We have to test it. We're nowhere close yet to testing this. But the ideas seem quite robust, so it's quite exciting. Do we live in the matrix then? And the answer is, at least in this sense, the answer is probably what we're seeing here is piece of part of a larger picture about quantum gravity yet to emerge. How central the matrix picture will be, I don't know, but it's certainly very tantalizing. So thank you very much. Stay tuned for more, and I hope at least some of this made sense.
Thank you, Clifford. I see we have some questions. Why don't you?
One burning question here. Space-time is quantized. You know, we're limited, of course, in the speed of light, okay? But that's because we're going through the space-time, kind of like a jet plane goes through the air. But in order to go faster than the speed of sound, it has to go between the molecules. So suppose space-time is quantized, and you could get between the quanta of space-time. Would you be limited by the speed of light?
That's a great question. My guess would be that, well, certainly one thing we do know with reasonable certainty, because we've had over a century of testing, is that macroscopically the answer is probably no. Now, what's going on down at, say, the Planck scale, if that's where quantum gravity shows up, is still a mystery. And so one could imagine maybe that there are effective sort of superluminal effects that happen when you're down at that scale, depending upon the details of the theory of quantum gravity, which we don't yet know. But being able to now actually go from here to Saturn faster than the speed of light because we're exploiting some quantum gravity effect, it's difficult to imagine how that would be consistent with what we already know.
Need that as an exercise for the student?
Right, right.
My question deals with gravitons, and we've had Lisa Randall talk to us about string theory, and surmises that gravitons are coming from coincident brains next to each other. That's why they're so hard to detect. That's why we don't know where they're coming from. What's your idea on that?
Well, yeah, you'll notice I didn't mention string theory at all in the talk, although I do work on that, and that's because I didn't pursue the graviton picture, and I hopefully carefully said that if you try and understand gravitons at the level of particles, it doesn't seem to work. But indeed, one of the great discoveries is the realization that relativistic strings are a natural way where gravitons can be consistently
they're waves
quantized.
as well. Yes.
So say again?
They're waves as well, aren't they?
They're
Gravitons are waves.
right.
as
Yes.
well.
Yes. Well, that's just a feature of quantum mechanics in general. But to your question, I think what Lisa was probably talking about was the idea, the framework that she and many others have worked on and tried to make sense of, that you can have, because of the discovery of brains, which are extended objects, you can have a different, let me say it this way. The forces, all the forces we talk about except gravity, there are scenarios in which they can actually exist on the brain itself. So that brain could be our four-dimensional universe, and they'd be combined, they'd be confined to living on that brain. Gravity can't be confined. It just spreads everywhere. That's mass energy. So you have the brain in some higher dimensional space-time, and what happens then is that gravity gets weaker because it can spread not just on the brain, but off the brain as well.
That's what she mentioned.
Yeah. I think it's a very natural scenario. It would be nice to turn it into, something that connects to observable physics. But it's one of the opportunities that working with string theory has given us.
Thank you.
Yeah, I have a question on your slide that talked about Hawking radiation, and you illustrated the spontaneous creation of a pair of particle, an antiparticle, in which one, I'm going to use the word, falls into the black hole. And yet, when I hear that, or when I hear that description, I'm thinking, well, that's going to make the black hole a little bit bigger. On the other hand, we have the other particle wandering off by itself, which shows up as radiation. So when I look at that, I'm thinking, well, just from sitting in a vacuum, the black hole is going to spontaneously get bigger while it emits radiation. But on the other hand, what I think happens is it's the opposite, in that the black hole gets smaller as it emits radiation. So what am I missing here?
There's another calculation to be done, which probably was beyond the scope of this lecture, which actually analyzes the energy conditions on that particle falling in. You can ask, from a point of view of an asymptotic observer, what its energy is, and you'll find that when it crosses the horizon, it's a negative energy particle, and so it takes mass away. So the details.
I missed that detail again.
Yeah. The details are not apparent in what I did here, and it would take a little bit longer to explain. But it's consistent for that reason.
I had another question on that same slide, in that you show the formula for the force of gravity, and in that formula you showed time. But in that spot, I thought that it should have time squared, and because when I see the force between two objects, the force between them diminishes with the square of the distance rather than the distance itself, or at least certainly it doesn't with the electromagnetic particles.
That's great, and that's because it was an energy equation. So instead of a force equation, which
okay.
is 1 over r squared, the energy is 1 over r.
I failed to trap it.
I love these exams.
That was a very nice lecture. Thank you.
Thank you.
One thing I was a little puzzled about, so you have these different surfaces, and you put the tessellation on them, then you draw the lines, then you make this field M that suddenly has n by n matrix. I don't, other than something that gets really big so I can do an expansion of 1 over n, what is M and why does it have n indices?
That's a great question. It is it emerges in exactly the route that I gave, which is that you do these tessellations, you're trying to count them, and then you realize that it's equivalent to counting in this totally other problem, which is this problem involving these matrices. So it's not like this M lives in space-time or anything like a field in space-time. It's just a different way of, if you like, getting the same mathematics. So we could then go, so we have this other piece of mathematics, and a part of that mathematics, when I take n large and I, squint a little bit, a part of that mathematics contains a description of all of these different surfaces that I need to describe space-time. But that thing is larger. It also tells us then how we might go beyond space-time, because it contains more than just those surfaces. So that's kind of the way we think about it. We've found a tool for modeling those space-times and then counting them in order to do the quantum problem. And then we then take the tool itself more seriously. It's telling us maybe more about at least the model of how the quantum aspects of the space-time can be captured as well.
Still don't see how you get that, what that M model is, but I'll ask you.
Yeah, well, it's one of those things, again, that only so much I could put on those yellow bits of paper without you all running screaming. So.
Yes, I think it was Wheeler that said that black holes have no hair because they have mass and charge, but I don't understand how the charge works. If two particles are created in space, typically they're plus and minus, and arbitrarily one goes into the black hole and all the information disappears, and the other one goes somewhere in the, okay. Is it possible the black hole can develop a charge? It seems to me it would neutralize.
So indeed, not by this mechanism, because you have every possible kind of particle and its antiparticle, coming from the vacuum. So the net change in charge is zero. So it's not going to accumulate charge in this way. There are other mechanisms by which black holes could produce accumulate charges if you have magnetic fields and things like that. And these are known problems, known mechanisms in astrophysics for producing some of the signals we see from the cores of galaxies. But it's not through this process.
It was toward the end, so I'm sorry I was probably not concentrating as well. But you said you were going to tell us what n is, and I just heard number. But is it a reflection of the number of small pieces that you use? Okay,
Yeah.
so I got that.
Yeah,
All
yeah,
right, it wasn't
yeah.
completely asleep.
I sped up a little bit on one slide where I had that, so it's not your fault. Yeah, but the point is that you could, let's pretend we were doing this for a real astrophysical black hole, and I'm not claiming that this works for that. These are much more toy models. But if you could measure the entropy, because it's a geometrical property. It's the area of the black hole divided by 4, it turns out, the formula. And then there's some constants of nature. There's an H bar and a C and a G. And so there's a number. It's a large number, but it's a number that, in principle is measurable for a black hole. But then we then find that is telling me if I have an entropy, it should be, turns out to be the logarithm of the number of degrees of freedom in those microscopic things. And so that's where the n goes. So you can equate those two things. This geometrical quantity then connects to this microscopic description. And that's really what's been driving the research program in quantum gravity for many decades, the fact that if this entropy calculation is true, and it seems very robust, there should be a microscopic description. And it should, according to Boltzmann, tell us about the number of microscopic states.
Okay, I think that's a good point to end. So let's.
That was one. I want to hear this question.
Sorry. One more.
Yes.
As you interpreted M as a matrix, what are its eigenfunctions and what's the interpretation for that?
That would take me longer, come up afterwards, but yes,
Thank you.
I could tell you more. Yeah.
Another good question.
Actually, it's an easy answer. Well, the eigenvalues are the energy states of the black hole, essentially. Kind of, sort of. Yeah. But I can say more.
Okay, let's thank Clifford again for wonderful lecture.